And we are back, and we are so back with systems with generic operations. So, in the previous section, we saw how to design systems in which data objects can be represented in more than one way. The key idea is to link the code that specifies the data operations to the several representations by means of generic interface procedures. Now we will see how to use this same idea not only to define operations that are generic over different representations, but also to define operations that are generic over different kinds of arguments. We have already seen several different packages of arithmetic operations. The primitive arithmetic built into our language, the rational number arithmetic of section 2.1.1, and the complex number arithmetic that we implemented in section 2.4.3. We will now use data-directed techniques to construct a package of arithmetic operations that incorporates all the arithmetic packages we have already constructed. Okay. Figure 2.23 shows the structure of the system we shall build. Notice the abstraction barriers. From the perspective of someone using numbers, there is a single procedure add that operates on whatever numbers are supplied. Add is part of a generic interface that allows the separate ordinary arithmetic, rational arithmetic, and complex arithmetic packages to be accessed uniformly by programs that use numbers. Any individual arithmetic package, such as the complex package, may itself be accessed through generic procedures that combine packages designed for different representation, such as rectangular and polar. Moreover, the structure of the system is additive, so that one can design the individual arithmetic packages separately and combine them to produce a generic arithmetic system. Let me see one thing. I want to be sure that I'm recording. Okay, I'm recording. So here we have the figure 2.23, and we see that programs that use numbers just need to use add, sub, mul, and div, and then we have different procedures depending on which kind of arithmetic we are dealing with. So let's start with generic arithmetic operations. The task of designing generic arithmetic operations is analogous to that of designing the generic complex numbers operations. We would like, for instance, to have a generic addition procedure add that acts like ordinary primitive addition plus on ordinary numbers, like add ret on rational numbers, and like add complex on complex numbers. We can implement add and the other generic arithmetic operations by following the same strategy used in section 2.4.3 to implement the generic selectors for complex numbers. We will attach a type tag to each kind of number and cause the generic procedure to dispatch to an appropriate package according to the data type of its arguments. The generic arithmetic procedures are defined as follows. So here we define this procedure. I had two numbers. We have this apply generic add xy, okay? Do the same for sub, mul, and div. We begin by installing a package for handling ordinary numbers, that is, the primitive numbers of our language. We will tag these with the symbol scheme number. The arithmetic operations in this package are the primitive arithmetic procedures. So there is no need to define extra procedures to handle the untagged numbers. Since these operations each take two arguments, they are installed in the table keyed by the list. Scheme number. Okay. Users of the scheme number package will create tagged ordinary numbers by means of the procedure. Yeah, make scheme number, get make scheme number. Now that the framework of the generic arithmetic system is in place, we can really include new kinds of numbers. Here is a package that performs rational arithmetic. Notice that, as a benefit of additivity, we can use without modification the rational number code from section 2.1.1 as the internal procedures in the package. Okay? Yeah, that's the same code that we have seen before. Okay, and this is the interface to the rest of the system. Okay. We can install a similar package to handle complex numbers using the tag complex. In creating the package, we extract from the table of the operations make from real image and make from mag-eng that were defined by the rectangular and polar packages. Additivity permits us to use as the internal operations the same add complex, subcomplex, mulcomplex, and div complex procedures from section 2.4.1. Okay, yes, we have seen this before. Programs outside the complex number package can construct complex numbers either from real and imaginary parts or from magnitudes and angles. Notice how the underlying procedures, originally defined in the rectangular and polar packages, are exported to the complex package and exported from there to the outside world. Okay? What we have here is a two-level tag system. A typical complex number such as 3 plus 4i in rectangular form would be represented as shown in figure 2.24. The outer tag complex is used to direct the number to the complex package. Once within the complex package, the next tag, rectangular, is used to direct the number to the rectangular package. In a large and complicated system, there might be many levels, each interfaced with the next by means of generic operations. As a data object is passed downward, the outer tag that is used to direct it to the appropriate package is stripped off by applying contents, and the next level of tag, if any, becomes visible to be used for further dispatching. Yeah, that seems straightforward. In the above packages, we use add-ret, add-complex, and the other arithmetic procedures exactly as originally written. Once these definitions are internal to different installation procedures, however, they no longer need names that are distinct from each other. And we could simply name them add, mul, sub, mul, and div in both packages. Okay, bunch of exercises. Okay. Combining data of different types. We have seen how to define. We have seen how to define a unified arithmetic system that encompasses ordinary numbers, complex numbers, rational numbers, and any other type of number we might decide to invent, but we have ignored an important issue. The operations we have defined so far treat the different data types as being completely independent. Thus, there are separate packages for adding, say, two ordinary numbers or two complex numbers. What we have not yet considered is the fact that it is meaningful to define operations that cross the type boundaries, such as the addition of a complex number to an ordinary number. We have gone to great pains to introduce barriers between parts of our programs so that they can be developed and understood separately. We would like to introduce the cross-type operations in some carefully controlled way so that we can support them without seriously violating our module boundaries. One way to handle cross-type operations is to design a different procedure for each possible combination of types for which the operation is valid. For example, we could extend the complex number package so that it provides a procedure for adding complex numbers to ordinary numbers and install these in the table using the tag complex scheme number. This technique works, but is cumbersome. With such a system, the cost of introducing a new type is not just the construction of the package of procedures for that type, but also the construction and installation of the procedures that implement the cross-type operations. This can easily be much more code than is needed to define the operations on the type itself. The method also undermines our ability to combine separate packages additively, or at least to limit the extent to which the implementers of the individual packages need to take account of other packages. For instance, in the example above, it seems reasonable that handling mixed operations on complex numbers and ordinary numbers should be the responsibility of the complex number package. Combining rational numbers and complex numbers, however, might be done by the complex package, by the rational package, or by some third package that uses operations extracted from these two packages. Formulating coherent policies on the division of responsibility among packages can be an overwhelming task in designing systems with many packages and many cross-type operations. Okay, seems clear. Coercion. In the general situation of completely unrelated operations acting on completely unrelated types, implementing explicit cross-type operations, cumbersome though it may be, is the best that one can hope for. Fortunately, we can usually do better by taking advantage of additional structure that may be latent in our type system. Often, the different data type are not completely independent, and there may be ways by which objects of one type may be viewed as being of another type. This process is called coercion. For example, if we are asked to arithmetically combine an ordinary number with a complex number, we can view the ordinary number as a complex number whose imaginary part is 0. This transforms the problem to that of combining two complex numbers, which can be handled in the ordinary way by the complex arithmetic package. Yes? In general, we can implement this idea by designing coercion procedures that transform an object of one type into an equivalent object of another type. And here is a typical coercion procedure which transforms a given ordinary number to a complex number with that real part and 0 imaginary part. I got the point, okay. And we install these coercion procedures in a special coercion table indexed under the names of the two types. Okay, we assume that there are put coercion and get coercion procedures available for manipulating this table. Generally, some of the slots in the table will be empty, of course, because it is not generally possible to coerce an arbitrary data object of each type into all other types. Now, for example, there is no way to coerce an arbitrary complex number to an ordinary number. So there will be no general complex arrow scheme number procedure included in the table. Once the coercion table has been set up, we can handle coercion in a uniform manner by modifying the apply generic procedure of section 2.4.3. When asked to apply an operation, we first check whether the operation is defined for the argument's types, just as before. If so, we dispatch to the procedure found in the operation and type table. Otherwise, we try coercion. For simplicity, we consider only the case where there are two arguments. We check the coercion table to see if objects of the first type can be coerced to the second type. I don't know how to pronounce this coerce word, but you can read it. So, well, let's do things in the right way. Let me search for this word coerce. Coerce.
Coerce.
Coerce.
Coerce.
Coerce. Coerce. Coerced. Coerce, coerced. Okay. We check the coercion table. What's coercion?
Coercion.
Coercion. We check the coercion table to see if objects of the first type can be coerced to the second type. If so, we coerced the first argument and try the operation again. If objects of the first type cannot in general be coerced to the second type, we try the coercion to the other way around to see if there is a way to coerce the second argument to the type of the first argument. Finally, if there is no known way to coerce either type to the other type, we give up. It is the procedure. Okay, I got the point. I got the point of all these. This coercion scheme has many advantages over the method of defining explicit cross-type operations as outlined above. Although we still need to write coercion procedures to relate the types, possibly n-square procedures for a system with n types, we need to write only one procedure for each pair of types rather than a different procedure for each collection of types and each generic operation. What we are counting on here is the fact that the appropriate transformation between types depends only on the types themselves, not on the operation to be applied. On the other hand, there might be applications for which our coercion scheme is not general enough. Even when neither of the objects to be combined can be converted to the type of the other, it may still be possible to perform the operation by converting both objects to a third type. In order to deal with such complexity and still preserve modularity in our programs, it is usually necessary to build systems that take advantage of still further structure in the relations among types, as we discuss next. Okay, so we have coercion, but we can also have hierarchies of types. Let me see. I don't want mispronounced words.
Hierarchy.
Hierarchy. Hierarchies. Hierarchies of types. The coercion scheme presented above relied on the existence of natural relations between pairs of types. Often there is more global structure in how the different types relate to each other. For instance, suppose we are building a generic arithmetic system to handle integers, rational numbers, real numbers, and complex numbers. In such a system, it is quite natural to regard an integer as a special kind of rational number, which is in turn a special kind of real number, which is in turn a special kind of complex number. What we actually have is a so-called hierarchy of types, in which, for example, integers are a subtype of rational numbers. A tower of types. We have a tower of types. The idea is any operation that can be applied to a rational number can automatically be applied to an integer. Conversely, we say that rational numbers form a supertype of integers. The particular hierarchy we have here is of a very simple kind, in which each type has at most one supertype and at most one subtype. Such a structure, called a tower, is illustrated in figure 2.25. And this is our tower of types. We have a tower structure, then we can if we have a tower structure, we can greatly simplify the problem of adding a new type to the hierarchy, for we need only specify how the new type is embedded in the next supertype above it and how it is the supertype of the type below it. For example, if we want to add an integer to a complex number, we need not explicitly define a special coercion procedure, integer arrow complex, but instead we define how an integer can be transformed into a rational number, how a rational number is transformed into a real number, and how a real number is transformed into a complex number. We then allow the system to transform the integer into a complex number through these steps and then add the two complex numbers. We can redesign our apply generic procedure in the following way. For each type, we need to supply a raise procedure, which raises objects of that type one level in the tower. Then, when the system is required to operate on objects of different types, it can successively raise the lower types until all the objects are at the same level in the tower. Another advantage of a tower is that we can easily implement the notion that every type inherits all operations defined on a supertype. For instance, if we do not supply a special procedure for finding the real part of an integer, we should nevertheless expect that real part will be defined for integers by virtue of the fact that integers are a subtype of complex numbers. In a tower, we can arrange for this to happen in a uniform way by modifying apply generic. If the required operation is not directly defined for the type of the object given, we raise the object to its supertype and try again. We thus crawl up the tower, transforming our argument as we go, until we either find a level at which the desired operation can be performed or hit the top, in which case we give up. Yet another advantage of a tower over a more general hierarchy is that it gives us a simple way to lower a data object to the simplest representation. For example, if we add 2 plus 3i to 4 minus 3i, it would be nice to obtain the answer as the integer 6 rather than the complex number 6 plus 0i. Inadequacies of hierarchies. If the data types in our system can be naturally arranged in a tower, this greatly simplifies the problems of dealing with generic operations on different types, as we have seen. Unfortunately, this is usually not the case. So figure 2.26 illustrates a more complex arrangement of mixed types. Yeah. Relations among types of geometric figures. These ones showing relations among different types of geometric figures. We see that, in general, a type may have more than one subtype. Triangles and quadrilaterals, for instance, are both subtypes of polygons. In addition, a type may have more than one supertype. For example, an isosceles right triangle might be regarded either as an isosceles triangle or as a right triangle. This multiple supertypes issue is particularly thorny, since it means that there is no unique way to raise a type in the hierarchy. Finding the correct supertype in which to apply an operation to an object may involve considerable searching through the entire type network on the part of a procedure such as apply generic. Since there generally are multiple subtypes for a type, there is a similar problem in coursing value down the type hierarchy. Dealing with large numbers of interrelated types while still preserving modularity in the design of large systems is very difficult and is an area of much current research. Okay, bunch of exercises. I think we are done. I think that this is the end. It is not the end. Let me see. Show sidebar. Systems with generic operations. Yes, that's the last section, and then we are done. And then we are done with chapter 2. Cool. Okay, let's continue. Symbolic algebra. The manipulation of symbolic algebraic expressions is a complex process that illustrates many of the hardest problems that occur in the design of large-scale systems. An algebraic expression in general can be viewed as a hierarchical structure, a tree of operators applied to operands. Yeah, this is a cool definition. An algebraic expression in general can be viewed as a hierarchical structure, a tree of operators applied to operands. We can construct algebraic expressions by starting with a set of primitive objects, such as constants and variables, and combining these by means of algebraic operators, such as addition and multiplication. As in other languages, we form abstractions that enables us to refer to compound objects in simple terms. Typical abstractions in symbolic algebra are ideas such as linear combination, polynomial rational function, or trigonometric function. We can regard these as compound types, which are often useful for directing the processing of expressions. For example, we could describe the expression blah 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 as a polynomial in X with coefficients that are trigonometric functions of polynomials in Y, whose coefficients are integers. We will not attempt to develop a complete algebraic manipulation system here. Such systems are exceedingly complex programs embodying deep algebraic knowledge and elegant algorithms. Yeah. What we will do is look at a simple but important part of algebraic manipulation, the arithmetic of polynomials. We will illustrate this kind of decisions the designer of such system faces, and how to apply the ideas of abstract data and generic operations to help organize this effort. Arithmetic on polynomials. Our first task in designing a system for performing arithmetic on polynomials is to decide just what polynomial is. Polynomials are normally defined relative to certain variables. The indeterminates of the polynomial. For simplicity, we will restrict ourselves to polynomials having just one indeterminate univariate polynomials. We will define a polynomial to be a sum of terms, each of which is either a coefficient, a power of the indeterminate, or a product of a coefficient and a power of the indeterminate. A coefficient is defined as an algebraic expression that is not dependent upon the indeterminate of the polynomial. For example, is a simple polynomial in X, and instead is a polynomial in X whose coefficients are the polynomials in Y. Already, we are skirting some thorny issues. Is the first of these polynomials the same as the polynomials or not? A reasonable answer might be yes if we are considering a polynomial purely as a mathematical function, but no if we are considering a polynomial to be a syntactic form. The second polynomial is algebraically equivalent to, to a polynomial in y, whose coefficients are polynomial in x. Should our system recognize these or not? Furthermore, there are other ways to represent a polynomial, for example, as a product of factors, or for a univariate polynomial as the set of roots, or as a listing of the values of the polynomial at a specified set of points. We can finesse these questions by deciding that in our algebraic manipulation system, a polynomial will be a particular syntactic form, not its underlying mathematical meaning. Now we must consider how to go about doing arithmetic on polynomials. In this simple system, we will consider only addition and multiplication. Moreover, we will insist that two polynomials to be combined must have the same indeterminate. We will approach the design of our system by following the familiar discipline of data abstraction. We will represent polynomials using a data structure called a poly, which consists of a variable and a collection of terms. We assume that we have selectors variable and term list that extract those parts from a poly, and the constructor make poly that assembles a poly from a given variable and a term list. A variable will be just a symbol, so we can use the same variable procedure to compare variables. Okay, so I think that this book has a problem. The problem is that in basically every example is an example drawn from mathematics. And if you know very well mathematics, it's easy to follow. It's easy to follow along, it's easy to understand. But otherwise, it's an additional layer of complexity on top, because you have to understand the general ideas and the philosophy of what the book is trying to say. But to do that and to follow the book, you also have to at least grasp what the examples are about. So you need to understand the math behind the examples. And I don't think this is a good idea. But we have started with this book, and I want to continue with this book and learn as much as I can. To incorporate polynomials into our generic arithmetic system, we need to supply them with type tags. We'll use the tag polynomial and install appropriate operations on tagged polynomials in the operation table. We'll embed all our code in an installation procedure for the polynomial package, similar to the ones in section 2.5.1. Okay? Polynomial addition is performed term-wise. Terms of the same order, so with the same power of the indeterminate, must be combined. This is done by forming a new term of the same order whose coefficient is the sum of the coefficients of the addends. Terms in one addend for which there are no terms of the same order in the other addend are simply accumulated into the sum polynomial being constructed. In order to manipulate term lists, we will assume that we have a constructor, the empty term list, that returns an empty term list, and the constructor adjoin term that adjoins a new term to a term list. We will also assume that we have a predicate empty term list that tells if a given term list is an empty, a selector first term that extracts the highest order term from a term list, and a selector rest terms that returns all but the highest order term. To manipulate terms, we will suppose that we have a constructor make term that constructs a term with given order and coefficient, and selectors order and coef that return respectively the order and the coefficient of the term. These operations allow us to consider both terms and term lists as data abstractions, whose concrete representations we can worry about separately. Here is the procedure that constructs the term list for the sum of two polynomials. The most important point to note here is that we use the generic addition procedure to add together the coefficients of the terms being combined. This has powerful consequences, as we will see below. In order to multiply these two term lists, we multiply each term of the first list by all the terms of the other list, repeatedly using mul term by all terms, which multiplies a given term by all terms in a given term list. The resulting term list, each for one for each term of the first list, are accumulated into a sum. Multiplying two terms forms a term whose order is the sum of the orders of the factors and whose coefficient is the product of the coefficients of the factors. Multiplying two terms, okay. This is really all there is to polynomial addition and multiplication. Notice that since we operate on terms using the generic procedures add and mul, our polynomial package is automatically able to handle any type of coefficient that is known about by the generic arithmetic package. If we include a coercion mechanism, such as one of those discussed in section 2.5.2, then we also are automatically able to handle operations on polynomials of different coefficient types, such as, because we install the polynomial addition and multiplication procedures add poly and mul poly in the generic arithmetic system as the add and mul operation for type polynomial, our system is also automatically able to handle polynomial operations such as The reason is that when the system tries to combine coefficients, it will dispatch through add and mul. Since the coefficients are themselves polynomial in Y, these will be combined. The result is a kind of data-directed recursion in which, for example, a call to mul poly will result in recursive calls to mul poly in order to multiply the coefficients. If the coefficients of the coefficients were themselves polynomials, the data direction would ensure that the system would follow through another level of recursive calls and so on through as many levels as the structure of the data dictates. Okay, I think we are basically done. I think we are basically done. Yeah. Okay. Representing term lists. Finally, we must confront the job of implementing a good representation for term lists. A term list is in effect a set of coefficients keyed by the order of the term. Hence, any of the methods for representing sets can be applied to this task. On the other hand, our procedures add terms and mul terms always access term lists sequentially from highest to the lowest order. Thus, we will use some kind of ordered list representation. How should we structure the list that represents a term list? One consideration is the density of the polynomials we intend to manipulate. The polynomial is said to be dense if it has non-zero coefficients in terms of most orders. If it has many zero terms, it is said to be sparse. Okay? The term lists of dense polynomials are most efficiently represented as list of the coefficients. For example, A above would be nicely represented as 1, 2, 0, 3, minus 2, minus 5. The order of a term in this representation is the length of the sublist beginning with that term coefficient, decremented by 1. This would be a terrible representation for a sparse polynomial such as B. There would be a giant list of zeros punctuated by a few lonely non-zero terms. A more reasonable representation of the term list of a sparse polynomial is as a list of the non-zero terms, where each term is a list containing the order of the term and the coefficient for that order. In such a scheme, polynomial B is efficiently represented as 101, 22, 01. As most polynomial manipulations are performed on sparse polynomials, we will use this method. We will assume that that term lists are represented as lists of terms arranged from highest order to lowest order term. Once we have made this decision, implementing the selectors and constructors for terms and term lists is straightforward. Okay. Hierarchies of types in symbolic algebra. Our polynomial system illustrates how objects of one type, so polynomials, may in fact be complex objects that have objects of many different types as parts. This poses no real difficulty in defining generic operations. We need only install appropriate generic operations for performing the necessary manipulations of the parts of the compound types. In fact, we saw that polynomials form a kind of recursive data abstraction, in that parts of a polynomial may themselves be polynomials. Our generic operations and our data-directed programming style can handle this complication without much trouble. On the other hand, polynomial algebra is a system for which the data types cannot be naturally arranged in a tower. For instance, it is possible to have polynomials in x whose coefficients are polynomials in y. It is also possible to have polynomials in y whose coefficients are polynomial in x. Neither of these types is above the other in any natural way, yet is so often necessary to add together elements from each set. There are several ways to do this. One possibility is to convert one polynomial to the type of the other by expanding and rearranging terms so that both polynomials have the same principal variable. One can impose a tower-like structure on these by ordering the variables and thus always converting any polynomial to a canonical form with the highest priority variable dominant and lower priority variables buried in the coefficients. This strategy works fairly well, except that the conversion may expand the polynomial unnecessarily, making it hard to read and perhaps less efficient to work with. The tower strategy is certainly not natural for this domain or for any domain where the user can invent new types dynamically using old types in various combining forms, such as trigonometric functions, power series, and integrals. It should not be surprising that controlling coercion is a serious problem in the design of large-scale algebraic manipulation systems. Much of the complexity of such systems is concerned with relationships among diverse types. Indeed, it is fair to say that we do not yet completely understand coercion. In fact, we do not yet completely understand the concept of a data type. Nevertheless, what we know provides us with powerful structuring and modularity principles to support the design of large systems. Okay, and I think we are done because this is a big exercise. Yeah. Okay, so in the next video, I think I will do a review of chapter 2, trying to summarize the important stuff and to highlight the key takeaways from this chapter. And then we will start with chapter 3, which is named Modularity, Objects, and State. So let's see you in the next video. Ciao ciao.